All right, as promised, these are going to be some examples of each of these different kinds of rational functions and how we can get a very accurate graph from just the stuff that we know and a little bit of knowledge of x and y intercepts that you're pretty familiar with. So our first example, and I'm hoping I have room, yes, I think I do. We'll just call it example 1. And I'm going to highlight it in the same color because I like colors. This is an example of one where, and it will go up here, where m is bigger than n. So meaning that the degree of the denominator is bigger than the degree of the numerator. So our function is r of x equals x minus 1 over x squared minus 4. So very clearly the degree of the denominator is bigger than the degree of the numerator. Okay, so we're going to start with vertical asymptotes. We learned that first, we might as well start with there, right? So vertical asymptotes happen where the denominator is equal to 0 because they are not allowed to equal 0. So asymptotes happen at those points. I will also point out that this function, it's not, well, let's factor it first. So x squared minus 4 factors, it's a difference of squares, and it factors into x plus 2 and x minus 2. So realize now that this is completely reduced, right? There's nothing that cancels from the top and the bottom. So anything that makes the bottom 0 is going to be an asymptote. So the two things that make that 0 are x equals negative 2 and x equals positive 2 for those two. So it has asymptotes at those 2 points. I will also indicate here the multiplicity of those asymptotes because that's going to help us graph it. So the multiplicity of both of these is just 1. They both only occur once. And I will just remind you really quick down here what that means. That means that the two bits of the graph will approach the asymptote from different directions. Okay, we'll do it like this. It's going to approach from different directions. So one will approach positively and one will approach negatively because that is an odd multiplicity of those vertical asymptotes. Next we're going to do other asymptotes, meaning either horizontal or oblique, right? And so I will just walk really quickly through this this idea here again with you that we did on the previous page. Our function says x squared minus 4 is dividing x minus 1. For really big numbers, that approaches just x over x squared, right? Just the leading terms are what actually matter in the end, right? And that reduces, because there's an x on the top and an x on the bottom, to be 1 over x. And when you plug in really big numbers to that, it's basically 0. So I will remind you that this is the first kind, right, where it always has an asymptote at y equals 0. So we now know that it approaches 0 when you go to infinity in both directions. So it has a horizontal asymptote at y equals 0. Other things we are really good to know is that is the x-intercepts and the y-intercepts of this, and they're really not too hard to get. The x-intercepts are found by, and I think I might need more room, so I'm going to move that guy down a little bit. X-intercepts happen where the numerator equals 0, because the denominator doesn't matter if the numerator equals 0. Dividing 0 by anything still gets you 0. So you set the numerator equal to 0, and that's what gets you your zeros, or your x-intercepts of this function. So the numerator in this case is x minus 1, and I'm going to set that equal to 0. I'm going to add 1 on both sides, and then it gets me the x-intercept at 1, right? And I might also add here, you'll see in a later example that the multiplicity of your x-intercepts actually helps you graph it as well. This is just using your knowledge of polynomials in general. The x-intercepts with an odd multiplicity cross the x-axis, and x-intercepts with an even multiplicity bounce off the x-axis. This one is odd, so just keep that in mind. I'm not going to write it because I am trying not to put too much information in here. For the y-intercepts, what we do is we plug in 0, because y-intercepts always happen at x equals 0, so we plug in x equals 0, which is a cinch, right? So our r of 0 equals 0 minus 1 on the top and 0 squared minus 4 on the bottom. So negative 1 over negative 4, which is positive 1/4. So we have a y-intercept at 1/4. We have so much information about this graph right now, so we have, and it's enough to actually graph it very well. So here's my axes there. My first thing I'm going to do is draw my asymptotes. I have a vertical asymptote at -2 and +2, so those will be here and here, about. I'm just going to write that they're +2 and -2. The other asymptote that I have is at y equals 0, a horizontal asymptote at y equals 0. I'm going to try that to get that on the x-axis. So that's at y equals 0. So there's a bunch of things here that, bunch of asymptotes, so we already have kind of a picture of what this might look like. We also have an idea of, because of the multiplicity of the vertical asymptotes, of where these things are going to be pointing. So we know that they're going to be pointing different directions here. Actually, you know what? I take that back. We're going to first plot the x-intercepts, and then we'll talk about the multiplicity of the vertical asymptotes. So we have an x-intercept at +1, so right there, and also a y-intercept at +1/4, which is really close to the y-intercept, or x-axis, but not quite. So using this sort of idea here, we know that it crosses the y-axis at 1/4 and the x at 1, so we know it kind of has to be shaped like this. So already we have an idea of the direction that these are going to approach the asymptotes. We know these guys have to go up and down. We can't really do the opposite without it making not really very much sense at all. Remember that rational functions can't have corners or cusps either, just like polynomials. And because we know that the other sides of the asymptotes are going to be the opposite direction because of the multiplicity of both x-intercepts, vocabulary. The multiplicity of both vertical asymptotes is odd. So this one is going to approach to the negative, and it's also going to approach that y equals 0 line as x gets less and less in the negative direction. And this one has to go upwards here because this one is going down, so this one has to go up. And we'll also approach that y equals 0 line as well. And we have this funky looking graph, and you might not believe me, but I promise that's actually what the function looks like when you graph it. But if you are curious, go ahead and type that into Desmos and see how close we were. This is going to be our process for every one of these. We're going to find x and y intercepts, and then both kinds of asymptotes, vertical and horizontal or oblique. And multiplicity matters for vertical asymptotes and also x-intercepts. It'll just help you get an idea of what the graph looks like. So that's our first example. I'm now going to do an example of this second kind that I highlighted orange, where m and n are equal, meaning the degrees of the top and the bottom are the same. So I have here, and I'm just going to make myself a template so that I don't have to write this much. Our function, and then what we do is we find the vertical asymptotes, The other asymptotes, the x-intercepts, the y-intercepts, and I'll just remind myself how to do both of those. For the x-intercepts, you set the numerator equal to 0, and for the y-intercept, you plug in 0. And then I'll just draw myself, actually I'm going to move this guy over a little bit so that I have room for a graph over here. Our final graph. Perfect, okay. Okay, that way I don't have to do all of that over again later. So my example is going to be one second, the computer locked again. Okay, my example is going to be, and I might actually move this guy over a little bit because it's kind of a big one. So we have 2x squared minus 8x minus 10 on the top, and 3x squared minus 12 on the bottom. Perfect. Okay, so vertical asymptotes. First, I'm just going to attempt to factor this. The only thing I really care about for vertical asymptotes is the denominator, so I'm going to leave the numerator alone for now. All I care is about the denominator. And I'm noticing from the denominator a 3 can be pulled out. And then now I have a difference of squares there, so I have something over 3 times x plus 2 and x minus 2. It's a difference of squares. And now I can tell what the vertical asymptotes of this are going to be. I'm just noticing that we probably should just double check that the numerator doesn't factor into something that can reduce. So I guess I will cave and do that. So the numerator has 2 that can be factored out. 2 times x squared minus 4x minus 5. Which then factors into x, so multiplies to negative 5, adds to negative 4 is x minus 5 and x plus 1. So no, it doesn't have anything that reduces. This gives us a horizontal asymptote at negative 2, and this gives us a horizontal asymptote at positive 2, the same from last time. Both of them have odd multiplicities, they only occur once, so just as a reminder, that means that they're going to approach from different directions, which is good information. The other asymptotes here, so this is a situation where the power, the degree of the numerator, and the degree of the denominator are the same. So if we do this sort of mental exercise of thinking what this is going to look like really far down the line, when x is either really big or really small, the only thing we're going to care about is the leading term. And then that reduces, because we have an x squared and x squared on the top and the bottom, it reduces to 2/3, which means that we have a a horizontal asymptote at 2/3. Which is good information also. So we have our asymptotes all figured out. Let's figure out the x-intercept. That just means we have to figure out where the numerator equals 0. We factored it down here. So we have 2 times x minus 5 times x plus 1 equals 0. So the values that will make this 0 are positive 5 and negative 1. Which both have just a single multiplicity, so we'll just keep that in mind. And then for y-intercepts, we plug in 0, so this is me plugging in 0. 3 times 0 squared minus 12. So that reduces just to be negative 10, not reduces, sorry, but there's a bunch of zeros, right? And then we have negative 10 and negative 12, which reduces, they're both negative and they both have a 2 in there, so 5 positive 5/6. So we have a y-intercept at 5/6. Okay. X-intercepts, y-intercepts, and asymptotes. I'm going to graph all of those first and then see what our graph is going to look like. So we have a positive 2 and a negative 2 asymptote. I'll draw those. We also have this funky horizontal asymptote at 2/3, which is really close to the x-intercepts, but not quite. There we go. There's that. So we have x equals negative 2, x equals positive 2, and y equals 2/3. And then we have the intercepts. There's one at 5, which is over here, I'm going to say, that's 5. And then at negative 1, which is here in the middle. And then there is a y-intercept at 5/6. So just a thought here, 5/6 is more than 2/3, so I'm just going to put that super close to the asymptote, but not quite on it. So here's what I'm thinking. The multiplicity of both of those vertical asymptotes are odd. And then I have this shape in the middle where it crosses the x and then the y-axis like that. So I know it's already sort of shaped like that, which means it probably approaches this asymptote negatively and that one positively, which then gives me a lot of clues about the other one because I know they have to be the opposite. So this one goes up and approaches the y-intercept that way. This one goes down and approaches the the horizontal asymptote is what I meant, that way. So another really funky looking graph, but pretty cool too, right? So this is the kind of situation where both of the numerator and the denominator have the same degree, which give us a fractional horizontal asymptote. I have too much vocabulary in my head right now. Awesome. Okay, so I'm just going to cheat a little bit and paste this third example down here. This is example number 3, and our function is going to be, and I'm going to have to move these over again. Nope. I'm trying to copy this all again so then next time I don't have to. Okay. Beautiful. This function is going to be x times x squared minus 9 over x squared minus 3x minus 4. So vertical asymptotes first. I'm going to just factor my top and bottom polynomials there so that I know if it reduces and where the vertical asymptotes are. So the bottom needs to be factored. Numbers up, multiply to -4, add to -3, that is -4 and +1. The top has an x, and then the x squared minus 9 is a difference of squares, so +3 and -3. Does not reduce, so our two asymptotes are going to be at x equals 4 and x equals -1. Both with the multiplicity of 1 again. Which means that they go different directions. This is just my reminder for myself later. So I will be honest, this one is the fun one. And I am being sarcastic. So when there is a bunch, there's like let me say that again. The degree of the numerator is 1 bigger than the degree of the denominator, then we have to do some fun stuff to find the other asymptotes here. So this means, a difference of 1 means you have to do some polynomial division, which is that thing that you learned hopefully on Khan Academy. which you might have learned it's very easy to make mistakes when you are dividing polynomials. It's not necessarily like mathematically difficult, it's just hard to keep track of stuff. Essentially what you do to find, remember this is a situation where we get oblique asymptotes that end up being not a horizontal line, it ends up being a slanted line, a line with a slope. So in order to find where that asymptote is, sorry, I'm finding my place, you need to divide the bottom from the top. You need to actually do this polynomial division, because already it is two polynomials divided by one another, but we need to like actually divide them. So the first thing I'm going to do is multiply out my numerator, because I have it separated. So I'm just going to multiply those. That gives me x to the third power minus 9x. So as we know, in polynomial division, you need to have each term laid out very specifically. So the numerator is going to go in here, and we don't have an x squared term, so I need a 0x squared term, and then we have 9x, and then we have 0 constant term, so I'm going to put that on the end as well. So both of those are not, we don't actually need to write them, but we do for polynomial division, we need those. Then we'll have the denominator, which is x squared minus 3x minus 4 on the outside here. So I'm just actually dividing these two values, polynomials, and I'm going to move this because it's going to be in my way. Okay, so my polynomial division skills tell me that I need to just focus on the leading term here. So I have x squared on the outside and x to the third power on the inside, which means that that really goes in x times, right? Because we can multiply the outside polynomial by x and get x to the third power, which then gives me minus 3x squared and then minus 4x, because I just multiplied the whole thing by an x. And then I'm taking the difference of those two. So x to the third minus x to the third is nothing. 0x squared, take away negative 3x squared gives me positive 3x squared. Be careful because you're subtracting the difference. Negative 9x minus negative 4x is really like adding 4x, which gives you minus 5x. And then you bring this guy down and start the whole process over again. So again, focusing on my leading terms here, I have x squared and 3x squared, which means that this will theoretically go into this about 3 times. So we have positive 3 up there 3 times, and then I multiply this by that value to get this. X to the third minus 9x, and then 3 times 4 is 12, minus 12. And then I subtract those two polynomials. That gives me 0, 3x squared minus 3x squared, and then we have negative 5x minus negative 9x, which is 4x, positive 4x. Careful about those signs. If you need to pause me and think about that, please do. Taking away 12x, taking away negative 12x gives you positive 12x. So this down here, and I'm going to change colors really quick, this down here is the remainder, which we've learned is essentially you write that as like 4x plus 12 over this value, because we haven't divided this number by that, right? It's like left over. We actually do not care about the remainders for this particular, in this particular situation, because we're looking for the equation of the asymptote, the oblique asymptote, which happens to be this right here. This is the equation for the oblique asymptote. So I'm running out of room down here, but the oblique asymptote, whoops, how you spell oblique? The oblique asymptote happens at y equals x plus 3. So that will graph a line which crosses the y-axis at 3, right, and has a slope of 1. So it will graph, that is going to be our oblique asymptote, meaning it's just a horizontal asymptote, and you'll see a little bit what that looks like in a second. When I say this is the fun one, I really do mean it. It is interesting. This is going to be highlighted in blue because it's a blue example. Okay, so last two things, we need to find the x-intercepts and the y-intercepts, which are the same as before. We already factored the numerator here. It was x times x plus 3 times x minus 3. And we set it equal to 0, and we get the x-intercepts of 0, and then -3, and then +3, each with the multiplicity of just 1. So they have odd multiplicity. That'll be useful in a second. And then our y-intercept, we just plug in 0. So we have 0, r of 0 equals 0 times 0 squared plus -9 over 0 squared minus 3 times 0 minus 4. That ends up just being 0 divided by -4, which is just 0. So we end up with a y-intercept of 0, which is good because we also have an x-intercept of 0. So you can't have just an x-intercept of 0, right? It's going to be both. Great. So we have so much information here to process. So first I'm going to just graph my asymptotes. We have an asymptote at +4 and -1. So here's going to be where my +4 is. And here's my -1. Then we have an oblique asymptote, which I will remind you is you go up 3 from on the y-axis, and that's where it's gonna cross, and it has a slope of 1, which just means up 1 over 1. So it's a really exactly diagonal line. So it'll cross both axes at 3. This is going to not be enough room. Annoying. There we go. We'll make that work. Here's that other asymptote continued. Awesome. Okay. We also have x-intercepts and y-intercepts to graph here. So we have an x and y-intercept at 0. And then we have one at -3, which is actually where that line crosses. And also one at +3, which happens here. I'm actually going to shift this asymptote over a little bit because it looks like it's not quite at -1. That's better. Okay, so here's the information that we have. What is kind of funky about this is that there is a x-intercept at the same place that an asymptote is at, which just means that the graph crosses that its asymptote there, which is perfectly allowed because it's not a vertical asymptote, it's an oblique asymptote, and graphs sometimes cross their asymptotes if they're not the vertical ones. So we have 2 x-intercepts, and both of them are on the bottom here. So I'm assuming here that we are going to have to go up and then back down to get this second asymptote or second x-intercept. And I'm going to try that again because it was not. So it's adhering to all 3 of its asymptotes there and getting that those 2 x-intercepts. I'm gonna try again because I want it to look like. Here we go. So that's the middle section. There's not really any other way to make it cross both of those lines smoothly, and also adhere to both of its asymptotes. So that's what we're going with. I will also note that these multiplicities are odd, so the opposite ends of these are going to have to be the opposite direction. And I apologize for having to graph it up in that corner that's past our work, but whatever. There's a better version on Canvas where it's not all congested. Anyhow, so the rest of this is that we just have to make it cross here, and then it also has to adhere to this asymptote eventually, and it can't cross it again because we would know. And this one also has to adhere to its asymptote. So our best guess is going to be it goes through there and then it loops back and, not really loops, but it comes back and adheres to that asymptote, and then this guy up here is just going to be like a little corner guy. That is our best guess. Some of this is kind of hard to tell. Like, does this line in the corner go through its asymptote and then back up? That's not something we can really tell with the information that we have. Usually it doesn't, so you kind of assume that it doesn't cross its asymptote unless you like know that it does. And this actually is the graph, even though it's also our best guess. It actually is what the graph looks like on the function. So if you want to check that out, you can go ahead and do that. Hopefully you know how I'm doing this detective work, like where I'm getting this information, right? So the two x-intercepts helps me know that it was going to be like kind of a upside down U shape, because you can't really go smoothly through both of those lines unless you adhere to both of your asymptotes unless you look like it looks like that. And if you're wondering about that, like try a couple of different directions just to see like what it might look like. Because the more you try it, the more this one is really the only option. And then this one, we knew that it was going to be different from this one, right? It approaches in the positive direction, and also it had to cross that line. And then it also had to adhere to its asymptote eventually. So it has that like little loop, and then it follows the asymptote. And this guy up here, we just assumed that it didn't cross the asymptote. We didn't actually know that, but we know that it does approach this asymptote in the positive direction, and then it has to approach this asymptote. So there's a little bit of wiggle room with that guy up there, but besides that, there's really no other options besides this. Hopefully that made sense. That was the nastiest one, I promise. Oblique asymptotes are funky, for sure. So I have one more example for you. I know this is like super long. We for sure have probably had to watch this outside of class by now, but and that's my fault for being behind. Well, but we are going to be so on time for the next test because I have learned my lesson. So one more example. This one is the kind of example where the numerator's degree is much bigger than the denominator's, more than one difference between the two. This is x times, our example for this one is x times x squared plus 2x plus 1 over 3x plus 1. Perfect. So for our vertical asymptotes, we don't really have to factor at all because the denominator is already as factors as it's going to get. And in fact, I can tell that there's not going to be anything that cancels that either. Just from what I can tell, the numerator is going to factor into. So I'm going to just pay attention to the denominator, and I'm going to say that equals 0 at, and I will just do this math really quickly so you know what's happening in my head. At x equals negative 1/3. So there's going to be an asymptote at x equals negative 1/3. And it has the multiplicity, only the single multiplicity, right? It only happens once. Multiplicity of 1. Other asymptotes. So this is the one where we're following these rules that we have on this page. This says it has no horizontal or oblique asymptotes, right? The only thing that we actually care about is end behavior on this one. Because there's so much of a difference between the degree of the numerator and the degree of the denominator, it's just going to end up being, the end behavior is going to end up being like basically the leading terms but divided by each other. Reduced essentially. So I'll show you what that looks like, and hopefully you will know more what I mean. So our function is x times x squared plus 2x plus 1 and 3x plus 1. So the degree of the numerator here is x to the third power because like these two things are multiplied together. So so that would be our like leading term. For the numerator, it would be x to the third power. We could multiply that out all the way, but we don't really need to because we can already tell it's going to be x to the third, and we don't need the rest of it. The leading term of the denominator is 3x. And that reduces to be x squared over 3, because one of those x's cancel, which makes us this line here, y equals 1/3 x squared. Same thing as this, right? X squared divided by 3 is the same thing as this. This is a parabola, but squished by a third, right? It's a third of its normal height. And I'm going to actually graph that now because why not? And it's also centered on 0, 0, so here's my 1/3 height parabola for myself. That is just going to determine its end behavior, and it kind of does act like an asymptote, although you can't really have asymptotes that are curved, which is why we call this end behavior. It just means that the graph, if you squint really hard, is going to look like the graph of this parabola. That will make more sense maybe when you see what this looks like. The end behavior is going to just look like this function. So the more you zoom out of this function, the more it's going to look like this. It acts very much like an asymptote. So we have that. Now let's find x-intercepts. So the numerator is x times x squared plus 2x plus 1 equals 0. I'm going to factor that. My numbers that multiply to 1 and add to 2 are x plus 1 times x plus 1, right? Both ones add to 2, multiply to 1. So we end up with a x-intercept at 0, and then there's 2 of the terms give us the x-intercept at -1. So that gives it an even multiplicity, a multiplicity of 2, which is going to be important for us graphing this. It's a very useful amount of information there. And then y-intercepts, we just plug in 0 into our function. The numerator r of 0. The numerator ends up being just 2 times 0. It does 0 because it's all multiplied by 0, but I'm going to write it out for all of our sakes. So the numerator is 0 divided by 1, which gives us just 0, so we have a y-intercept at y equals 0. It's important. So all of those y-intercepts graphed. Here's the y-intercept of 0 and the x-intercept of 0 both at once. And then there's a multiplicity 2 intercept at -1, right there. Other information that I haven't graphed yet is that there's a vertical asymptote at -1/3, which is just barely past the y-intercept there. So that's also an asymptote. So also I will note that this intercept here has a multiplicity of 2. It's an even multiplicity, which we know from polynomials means bouncing. It doesn't go through that x-axis. It bounces back up, basically. So knowing that, and knowing that the end behavior has to be like this, right? It has to look like that parabola. We know that bouncing from that point will give you this formation there. It has to adhere to that vertical asymptote. The vertical asymptotes can't be crossed, so it has to go upwards that direction. Knowing that this multiplicity is 1 means that now the other direction, it's going to go downwards from that asymptote, and it also has to adhere to this end behavior. So we get a function that looks like this, where, and I maybe will show you this on Desmos just so you can see sort of clearer what's happening, because this function looks like a parabola, looks like 1/3 x squared, except for that it has a weird asymptote in the middle. So let me just show you that really quick. Actually, first I'm going to highlight this in dark blue because that is the color that I chose from the other page. This is a situation where the numerator degree is much bigger than the denominator degree. We end up with end behavior instead of asymptotes. Beautiful. Okay, so that's all I really have for you. I'm just going to show you super quick what that looks like. Oops, it's not the right one. I'm going to graph y equals x times x squared plus 2x. I'm just typing in that function for you. Plus, not minus, plus 1. All divided by 3x plus 1. Okay, so see this? There's like, it looks like a parabola. It looks like 1/3 of x squared, but then it has this funky asymptote in the middle. This is its x-intercept where it bounces, and this is its x-intercept where it crosses. So even multiplicity for that one, odd multiplicity for this one. Fun stuff. So that is how you graph rational functions. Please let me know if you have questions. I know that I'm home today because of my second COVID shot, but feel free to email me. I'd be happy to help you with any of these example problems. This is super important to internalize now and quickly because the test is coming up and you will need to know how to do this for the test, which is why I encourage you